domination, or it is getting what dominated by some another force, right? So then there comes this nuclear force, and this nuclear force is responsible for all this stability of nucleus. So these protons and these neutrons are sticking together because of this force. So this is the force which attracts these neutrons and protons together, right? And that is how they make this nucleus. So now, when this force acts, this nuclear force is a very short range force, right? It acts in one Fermi region. So whenever the separation is in Fermi order, then only this force will activate. Otherwise, if you increase the distance and if this is out of the order of Fermi, then this force will disappear, right? This force will only activate if the distance between the two two neutrons and protons and protons. So if these have the separation which is in the Fermi range, then only this nuclear force will be active. So that is how we know that this nuclear short range, right? And this is also called a strong force. This is a very strong force which helps these protons and neutrons. And what is this of nucleus? That we already know. That nucleus consists of neutron and proton, and they are together called nucleons, right? So whenever I will say nucleons, so I mean that these are neutrons and protons, right? And then what would be the energy, right? So what would be the energy that we would be talking about? Yes, hello Aisha, assalamu alaikum. Yeah, so we are just recapping because in the last class, if you remember, Mariam got disconnected. So we are just recapping what we did, right? So first thing that we did was, first thing we understood about this nuclear force. This is a short range force, acts between neutron and neutron, proton and proton. But it acts only when the separation is in the Fermi range. So the size that we'll be talking about would be in Fermi range, and then the energy unit that we will be talking about is mega electron volt, which is 10 to the power 6 electron. And then we also talked about the unit of mass. So unit of mass in this chapter that we will be taking is 1 U, which is 1 atomic mass unit, and it is equivalent to the 1 by 12th of the mass of this C12 atom. So the isotope of C12 atom, observe this. So this is 1.66 into 10 to the power minus 27 kg. So this is the mass of 1 U. And then we write the mass of different constituent elementary particles. So mass of the proton is this much, which is equivalent to this U, and then mass of neutron is slightly larger. It is comparable to mass of the proton, but slightly larger, and this is equivalent to this unit. And then mass of the electron is less. So this is equivalent to this atomic mass. And then we also talked about the mass of hydrogen atom. The mass of hydrogen atom consists of electron and proton. So that thing is 1.0078 U, right? And then we talked about the representation of the element. So we represent this X element, right? The superscript is A, the subscript is Z, right? And this A is called the mass number, which consists of neutrons and protons. Z is number of protons, right, which is also called atomic number, and number of neutrons, which is also denoted by capital N. So this we can right. So this we can denote it by capital. This we can then we can represent as it. And then we also talked about isobars, isotopes, right? Isobars, so same atomic number, but same atomic masses or mass number, but different atomic number. That is isobar. And then we have isotopes, so same atomic number, but different mass. And then we have isotones, so same atomic number, but same neutron number, but different atomic numbers. So these are the three kinds of things that we studied, right? And then lastly, we talked about this size of the nucleus, right? So in the last class, we talked about the size of the nucleus, and it varies over a to the power 1 by 3, which where a is the mass number, and this is the radius of the nucleus. And then depending upon the nucleus, radius of the nucleus, we calculated the density of the nucleus, and we saw that this is constant. Oh, who has written in the chat? Oh, please fix your cam. Okay. What is happening with my cam? Check that. Okay. Ah, okay. So density of the nucleus, which we found that the density of the nucleus is constant. So these are the things that we did in the last class, right? Now let us continue from here. So the next thing that we will study is about the mass energy relation, right? So if we calculate, right, so this is given by Einstein, Einstein's mass energy equivalence. So Einstein told that let's say we have some amount of mass, and how much energy that mass can give, that is given by this energy mass, right? So what does it say? So energy is mass and c square, right? And this is called the Einstein's mass energy. So let us calculate for one u, right? So for one atomic mass, what would be the mass energy equivalence, right? So for one atomic mass unit, what is the energy? So let us calculate, right? This would be how much? So if we calculate the energy, 1 U is how much, guys? How much is 1 U? How much is 1 U? Yes. So this in the last class we studied that this is 1.66 into 10 to the power minus 27. Right, so we put this value, we know that this is mc square, and mass is how much? Mass is 1 U. So for 1 U mass, what would be the energy equivalent to that? So m is 1 U, and c is how much? This is 3 into 10 to the power 8, and 3 into 10 to the power. This is c square. And this would be in what? this would be in joules. So this is how much? 1 U is 1.66 into 10 to the power minus 27 into 3 into 3 into 10 to the power 16 joules. Now we want to change it we know that what is the unit of energy in this chapter that we will take. So that is electron volt, right? And 1 electron volt is 1.6 into 10 to the power minus 19 joules. So if we change this joules to electron volt, so that would be how much? So that would be 1 divided by 1.6 into 10 to the power minus 9 electron. So that would be 1 joule. So if we put this value in here, so that would be how much? 1.66 into 10 to the power is into 9, and this is minus 27, and this is how much? So 10 to the power minus 11 divided by this 1.6 into 10 to the power minus 19 electron, right? So this would be how much then? So this, if we divide this thing, so this is, let us multiply this, just this thing, 1.66 into 9 and divided by 1.6. That is 937, right? And into, so this is into 10 to the power minus 11 plus 10 to the power, so this is 9 point, right? And plus 90 electron, this would be how much? So this is 933 and 7 into 10 to the power. This is how much? 8 electron volts. And this, if we write, so this is powers 8. And if we take 2 powers from here, right? So if we take 2 powers from here, so this would be 10 to the power 6 electron. So how much would be this thing? This is 933.75 into 10 to the power 6 electron volt. So how much is this thing? What is this value? This is 10 to the power 6. And we have already studied that what do we write 10 to the power 6? So 10 to the power 6 is mega electron, right? So yeah, so if we write this thing, and this is generally given by, so we are getting a small correction. So this is 935.1 into 10 to the power. We're getting a slightly different value. So conventionally, it is 935.1, right? How much is the value? 931.5. Yes, this is actually 90. We are getting a slightly different value, right? So if we have this is the 931.5, and this is mega electron, right? So this is the energy of the mass, which is mass is 1. So whenever you have 1 U mass, so its energy would be equivalent to 931.5. We are getting a different two value different, but yeah, so this would be because we have used this 1.605. If we use that, so then we get yeah, right. This is 1.605, and if we use that, so we'll get the correct answer, right? So actually, this is 931.5 mega. So this is the mass energy equivalent of 1 unit mass. Is it clear, guys? Is it clear?
Yes.
Yes, sir.
Then please note it down. And remember, this is very important. We will be using this thing very regularly, right? So in our every calculation, we'll be using this thing. So please remember it, right? Whenever we are writing the mass in this thing, so we can directly write its energy equivalent, right? Okay, you guys, please note it down. And let me check in the meanwhile that where did we do the order mistake? Right? 1.6. Yeah, so this is, if we use this, we have used 1.6. So if we use 1.605, then we'll get a 931.5, right? So there is a slight order difference. Whenever you guys have noted, please tell. Yeah, so this is given in example 13.3 also. That how much is this? Right? We have the charge. Charge is 1.602 into 10 to the power minus 19. And this 1U is 1.6605 into 10 to the power minus 20. And if we use these two, then we will get 951.5. But this is also correct, right? You can use this thing also, but this is the correct one. This is correct up to three significant figures, right? Okay, whenever you guys have noted it down, please take. Whenever you guys have noted,
Done, sir.
then what about you, Aisha? Then
Done.
yeah, and use this value, right? Don't use this value because we have approximated this thing to two places and this is to one place. That is why we have got this much. So this is slightly two order difference. This is the correct value, right? So whenever with the mass or the mass is written in unit, this atomic mass unit, then we can directly write as 931.5. Okay, so then we have this nuclear energy. What is this nuclear energy? So the energy corresponding nuclear nuclear force of attraction between the nucleons, right? Nucleons are what? They are neutron and protons. So this is the nuclear energy, right? And this nuclear energy is used in where? So, example, this is used in making a very destructive thing, which, right? So this was used in right in making atomic bombs, very destructive thing, and this is also used in nuclear power plants. And so this nuclear energy has a very important role in this place, but this has a destructive role in this, right? Some things have positive things and negative. Okay, so this is nuclear energy, and then we have this binding energy. Before we do this binding energy, let us understand about mass defect. So, what is this mass defect? Right. So, let's say that if you have a nucleus, right? If you have a nucleus, and let's say it has two neutrons or two protons and three neutrons, right? So, what should be the mass of this nucleus? What should be the mass of this nucleus, guys? What should be the mass of this nucleus? So, the mass of this nucleus should be, let's say, the mass of proton. So, we multiply it by 2, and then 3 neutrons. So, we multiply it by mass of the neutron. So, this should be the mass of the nucleus, right? Clear, guys?
Yes.
But when experimentally the scientists measured the mass of the nucleus, so they got a slightly lesser value, right? So when they measured the mass of the nucleus, then they got a very different value, and this was lesser than this thing, right? So let's say that this has 3 grams of proton, and let's say 4 grams of neutron, right? So this is neutron, and this is proton. So the value or the mass of the nucleus should be 7 grams. But the mass that they got was 6.5 grams. So there is a defect. How to write defect? Yeah, double. So there is a defect in the mass, right? And this defect in the mass is called the mass defect, right? So what is this mass defect? So uh, the discrepancy between the total mass of proton and neutron and the actual mass of the nucleus is called mass effect, right? So how do we calculate this mass defect? Right. Let's say we have an atom. Right. We have an atom which is this, or we have a nucleus. Right. So we have a nucleus whose atomic number is A, mass number is A, and atomic number is Z. Right. So then, if we calculate the total mass of proton and if we calculate the total mass of proton and neutron, right? So in this nucleus, how many protons are there? In this nucleus, how many protons are there? Yes, Z. So Aisha is saying Z. Is it correct, Mariam? Is
Sir,
it?
can you repeat
So I'm
your voice?
asking,
I
I'm
didn't hear
asking,
you.
yeah, I'm asking that what would be the mass of the proton, or how many protons are there in this element or in this nucleus? How many protons are there? Yes, Aisha is saying there are Z number of protons, right? So that is, so the number of protons would be Z, right? So if I calculate the mass of the proton, total mass of the proton, so let me write it as this would be total mass of proton plus total mass of neutron, right? So first let us calculate what is total mass of proton. So that would be how much? Let's say that we have what is the total mass of proton. So we have Z number of protons, and if we multiply by one mass of the proton, so this would be the total mass of the proton, right, guys? Right.
Yeah.
And what would be the total mass of neutron? How much would be that? So we have to find out how many neutrons are there and then multiply it with the mass of the neutron. Right, guys? Right. So how many neutrons are there in this nucleus? How many neutrons are there? How many neutrons are there? Yes. How many neutrons are there, guys?
Yeah.
A is mass number, right? A is mass number. Mass number is protons plus neutrons. So number of neutrons, that would be A minus Z, right? That is the number of neutrons. And then we multiply it the mass of the one. So this would be the total mass of neutron, guys, right? Right, guys? Why this is right? Why this is right? Why this is right? Well, it's right. Okay, so then if we calculate the total mass, so this total mass would be how much? That is ZMP plus A minus Z M. This is the total mass, and mass of nucleus that is represented by Mn, right, of let's say X A Z nucleus, right? So this is how they represent the mass of the nucleus. So mass defect, that would be how much? That would be Z MP plus A minus Z Mn minus M, right? So this is how we calculate the mass. Okay. Now let's say that this mass of the nucleus is not given, right? This mass of the nucleus is not given, but they have given the atomic mass, right? They have given the atomic mass. So then how do we calculate the mass defect? So to calculate that, we can change this mass of the nucleus to the atomic mass, right? So Aisha, you tell me that the atom will consist of what kinds of things? So if we have this atom, right? Let's say you have an atom. So this consists of what? So this atom is consisting of the nucleus and then the electrons, right? Right, Aisha? So if I calculate the mass of the nucleus, I want to calculate. And let's say there are how many electrons would be there? So there would be Z electrons, right? So Z number of electrons. So if I want to calculate the mass of the nucleus, so that would be how much? That would be atom, mass of the atom, right? That would be mass of the atom minus Z number of electrons. So this would be the mass of the nucleus. So if I put this value in here, so what I will get? If I put that value in here, so I will get ZMP plus A minus Z Mn minus this Mn I can represent as Ma minus Z M, right? So if I break this, so if I break this Ma and this bracket, so I'll get Z M, right? So we see that the Z and Z are common. So if we bring this thing in here, so this would be Z and MP plus ME. And this is A minus Z. And now we have mass of now we have mass of this atom. Instead of mass of the nucleus, you are given a mass of the atom. What is this thing, Aisha? What is this thing? What is this thing? Mass of proton plus mass of electron. What is this thing? If you remember, yes, mass of the hydrogen, right? Absolutely correct. So this is mass of the hydrogen plus A minus Z Mn and minus Ma. So this is another form of mass defect, right? And in this one, what you will be given? You will be given atomic mass. In this one, you will be given nucleus mass. So whenever the nucleus mass is given, then we use this mass defect. Whenever the atomic mass is given, then we use this mass defect, right? Where we already know that mass of the proton, that is how much? That is 1.0073 U. We know that mass of the neutron is 1.0086 U, and we also know that mass of electron is 0.00055 U, and mass of hydrogen, that is how much? 1.0078. So these things we have to remember. Okay, are these things clear to you?
Yes.
Then please note it down. Those these are very faint, right? Can you see this thing? Is this visible to you?
Yes.
Oh, then please note it down. Right. Please note it down, and then we'll talk about. Then we'll do some calculations, and then we'll talk about the other one. Right. And whenever you want me to scroll down, please that. Yeah, whenever you want me to scroll down the screen, please. Yeah. Then please note down. So I will write everything, right? So what are the this this is mass of proton, right? And ME is mass of electron, and then we have mass of N. This is mass of neutron, and then we have Mn. This is mass of nucleus, and then we have Ma. This is mass of atom. Right. Conventionally, in the book, they have this mass. They have represented it like this. So whenever you see this kind of thing, so you just assume that this is the mass of the atom that they have. This is atom. Yeah, whenever you have completed noting it down, please.
Yes.
Yeah. Okay, so now we can talk about this binding energy, right? So what is this binding energy? So the energy required to completely break the nucleus into protons and so that is what we call the binding energy, right? And this is so this binding energy is what? So so it is the energy released when the nucleus is formed, right? So this is what we call the binding energy, right? Due combination of protons and neutrons. So whenever the protons and neutrons come together and they form a nucleus, then some amount of the energy is released during that process, right? And that energy released causes the defect in the mass, right? So let's say that 2 gram of proton and 3 gram of neutron, right? They are combining together and they are making a, let's say, 4.5 gram of nucleus, right? Then some amount of this energy is released. 0.5 gram energy is released, and this energy is called a binding energy, right? So that is why you have this mass defect of this nucleus. Some amount of energy is released during that process. So can you guys tell me, we have two kinds of thermal process. One is exothermic and the other is endothermic. So this is what kind of process? This is what kind of the process? This energy is released. This is what kind of process? Yes, yeah. What kind of process is this? Is it endothermic or is it exothermic? What kind of process is this? So it is because energy is released, right? In what process the energy is released? Exothermic. So it is an exothermic process, right? These are the things that we understand about binding energy. And how do we calculate the binding energy? So to calculate the binding energy, we multiply the mass defect, right? This is the mass, and then we calculate the energy equivalence. So this is the binding energy, right? And this comes in joules, but we already know that if the mass are given, right? So if the mass or masses are given in atomic mass unit, then what? So then you write the binding energy directly equal to delta M, whatever the mass defect in U, and then 931.5 M. That we have already calculated. So this is a very important relation and always remember this. Right. This is how we calculate the binding energy. And binding energy for nucleon, so there is another thing which is called binding energy for nucleon. What is the binding energy for nucleon? So this is defined as the ratio of binding energy and the mass. Right. This is how we did the binding energy for nucleon. Binding energy for nucleon, and this is binding energy divided by A. So that is how we write the binding energy for nucleon. Okay, so you guys note it down and then we'll do some questions and then it would be very easy to understand. So please note down this part. Yes, Mariam, you got disconnected. So at what point you got, yeah, Aisha, please wait a moment. At what point you got disconnected, Mariam? In the mass defect, you got disconnected, right? In the mass defect, you got disconnected, right? Right, Mariam? Yes, can you hear? Oh, so Mariam's mic is not working. So then, yeah, please note down this part. Aisha, you please note down this part. And then, yeah, we will do some question and then it will be very easy. This is the second last topic, and then we have nuclear reactions, and then that would be right. Then this chapter will be complete. Please quickly note it down, and then some questions, and then this will be. Yes, whenever you guys have noted it down, please tell. Yes, noted, guys. Yes, guys, noted.
Yes.
Now let us do one question, and we will do few questions, and then we will move on to then this chapter will be finished. So let's say that to find the energy per nucleon of this atom where mass of this atom is given as how much is mass? 55.9. Right, so these are the masses which is given, and you have to find out the binding energy per nucleon. So we know that what would be the binding energy per nucleon, right? We have to first calculate the mass defect and then multiply it into 931.5 because these masses are given in U, right? So we have to find out first what would be the mass defect of this thing. What would be the mass defect? That would be ZmH plus because the atomic mass is given, right? Atomic mass is given, so then we will use this ZmH plus A minus Z Mn and then minus of M mass of this thing, Fe and 56 and 26. So what is the Z of this thing? Well, how much is the Z? How much is the Z of this atom? How much is the Z? So if we compare it with X, A, and Z, and this is Fe and 56 and 26. Z is 26, A is 56, and mass of the hydrogen that we already know that is 1.0078 U. Mass of the neutron that we already know 1.0086 U, and this mass is already given. Mass of Fe 26 56 that is 55.9. So these things are given. So if we put all these values, so this would be Z is 26 and into 1.0078 plus uh, 56 minus 26 and 1.0086 minus 55.9. This is how much? Then we have to use the calculator, right? How much is this? 26 into 1.078. That is 26.08 plus this is 30 into 1.086. That's 30 into 1.086. That is minus 55.9. This is 30.58 and this is 26.0 plus 26.08 and minus, this is coming out, this is how much? This is 56.4608 minus 50.93. So minus 55.9. This is 0.526. So the mass that we have got is this much unit. And whenever this unit is given in U, so then we can directly write its equivalent energy, right? So the binding energy, that would be how much? That would be 0.5268 into 931.5 and mega electron. So how much is this? Into 931.5. So that is 490.7142 mega electron. So you guys can think that how big this value is, right? 490 mega electrons. This is a quite large value. This is the binding energy. And if we calculate the binding energy in nucleon, which is binding energy by A, so this is 490.714 divided by A is how much? A is 56, right? 56, this is divided by 56. So 8.762 mega electron, right? This would be the binding energy part. So is it clear, guys? Is this question clear? Is it clear, guys?
Yes.
Please note it down. Uh, And in the next class, we'll start semiconductors. So that will take only one class, 1.5 class to complete that. So in next class or so, the chapter would be over, and then we'll start this. So these are very important because these may be asked in 3 marks questions. These are important calculation. These are straightforward, direct calculations. Comes very handy, right? We have to do all these values. You guys would be given the calculators, right? So calculate all these things. So you guys can use calculators. Yeah. Yeah, whenever you guys have noted. whenever you guys have calculated.
Yes.
Done. Okay, so then let us understand about the last topic, right? So the last topic is nuclear reactions. There are mainly two kinds of nuclear reactions, and in nuclear reactions, what do we have? Whenever we have a nuclear reaction, right? So there are, let's say, two elements, right? They are combining together and they are forming different elements, right? So this is some nuclear reaction, and then if some amount of energy is released, so that we'll talk about later, right? So these are reactants, and then these are products, right? So there is this Q value, right? So Q value of nuclear reaction. So how do we calculate this Q value? So this is given by the mass of A plus mass of the B minus, so this is mass of reactant minus mass of the product and its energy equivalent. So this is how we calculate the Q value, right? And then we talk about two kinds of nuclear reactions. What are those? So one is called nuclear fusion, and the other one is nuclear. Right. So what is this nuclear fusion? So when two light elements combine form a heavy element, then this kind of nuclear reaction is called nuclear. Right. Example, two hydrogen combining form helium 24 nucleon. So this happens at the Earth surface, and some amount of energy is right. So this in this process, a very large amount of energy is released, and that energy is used in different processes, right? So we have this hydrogen bomb also, so that uses the idea of this nuclear fusion, and then we have this nuclear fission. So what is this nuclear fusion? When heavy element is or element breaks into lighter element. And this kind of here reaction is called nuclear fusion. Fission. And example, breaking of Yeah. Okay. Right. Into krypton and bromine they break, but yeah, that part is. So these are the kinds of nuclear reactions that we have. And then this chapter is right. We should in the syllabus. This is not in detail that we have to study all those nuclear reactions, right? So that part is omitted, and we just have to remember these definitions, right? So please, you guys, note down this part, and then again we'll solve some problem in this chapter. So in the next class, we'll start the new chapter, which is chemical. So please note down this part. Please note down this part, and then in the next class we'll talk about chemical. Yeah. Okay, so now for your practice purposes, let us do some questions. I think that yeah, paper in here or questions in here. That, that is why they were so. Okay, so all these questions are very important, right? Let us do this 13.1 question. First question. So in this question they have given, right? We have to obtain the binding energy of this nitrogen nucleus, right? So we have to find out the binding energy of this nitrogen nucleus and mass of this nitrogen atom that they have given, right? Mass is the mass of nitrogen is 40, and this is 40.0. This mass of the nitrogen atom that they have given, and we have to find out the binding energy of this. To calculate the binding energy, we remember that this we have to find it in mega electron volt. So we have to find out this delta M of, right? And then we will multiply it by 931.5. That would mean in mega electron. So let us find out this delta M. That would be how much? That would be ZMH plus A minus Z Mn and minus this mass of this this atom. Okay, yeah. Okay, this who is please why? So Z is how much? Z is 7 and MH we already know that is 1.0078 and A is 14 minus 7 and Mn is 1.0086 minus this is 14.0037. So this is how much? Again, we have to use the calculator. So you guys practice these questions, right? At 7 into 1.0078, that is 7.0546 plus 7 into 7 into 1.0086. That is, right, I will directly write, that is 7.0602 minus 14.007. This is how much? Plus 7.056. This is 14.1148 minus 14.007 minus 14.37. This is 0.11173. This is the mass defect. And if we want to calculate binding energy, so this is simply 0.1173 equal 1 into 951.5. This is into 951.5. So 104.076 mega electron. This would be the binding energy. Is it clear, guys? Yes.
Yeah.
Yeah, quickly note it down and then we'll stop. And you guys also practice these questions, right? Practice these questions at your home. I will assign these homeworks to you. And if you guys please, whenever you guys have noted it down, please, yes, whenever you guys have noted, yes, noted, guys.
Done.